So far the course is focused on crystalline semiconductors, wherein we had a periodic arrangement of atoms, and we developed models such as the chronic penny model, wherein we used Bloch's theorem to identify a density of states profile. And in particular we looked at the density of states for 3D materials, 2D materials, etc. And we identified a energy, a density of state distribution, wherein we had states above the conduction band edge and below the valence band edge, but then no states inside a band gap. And now we reach the last bit of the course, wherein we are going to generalize all these ideas that we developed for crystalline semiconductors, and in particular talk about non-crystalline semiconductors. So what happens if the semiconductor is amorphous, for example? What happens if it has got a large number of defects, and what is the physics that governs this, and how do we build devices out of this, and how do we model and study the transistors based on such materials. So we now look at the device which sort of defines non-crystalline semiconductors, and in particular we look at something called as a thin film transistor. So what are the applications of non-crystalline semiconductors? The strongest application is in the development of something called as large area electronics. So let us consider a display screen. Okay. Now if I have to build transistors etc. on a substrate that is as large as a display screen, for example a display screen is several inches to even several feet in length, and if we need to build all the semiconductors and electronic devices that are present on the screen using crystalline silicon, one would require either a large tile of these crystalline materials, or one would require a very large wafer, and both these are going to be quite expensive, and it is probably not the best way to go about building such a large area system. So what is normally done is, in order to develop these kind of large area electronic systems, one starts with a substrate, okay, and this substrate is not a semiconductor wafer, but it could be any material, for example glass or even plastics. And on this substrate the different layers of your semiconductor device, or the different materials used to build your electronics are deposited as thin films. Okay, so for example if one needs to build a MOSFET on this large area substrate, this is one possible method that it could be done. We first develop a thin, we first deposit a very thin metallic film that will constitute the gate of the MOSFET. We will then deposit an insulator, a thin film that constitutes the insulator, and then a thin film that constitutes the semiconductor, and this would constitute the metal insulator semiconductor stack. And then we have our source drain electrodes, which if required would need the doping of the semiconductor or some kind of treatment in order to ensure low contact resistance and a good injection of carriers. So by depositing these various thin films using processes such as thermal evaporation for metals, or DC sputtering, or RF sputtering for semiconductors or insulators etc., we develop these thin films of, with each layer being about 50 nanometers, thin films of these materials to develop electronic devices. So by doing this over large areas and at low temperatures, one develops larger electronic systems for these various applications. Now the problem of using these kind of low temperature processes, or is that we often end up with semiconductors that are not crystalline. So for example if you take a material and you give all the atoms of the semiconductor enough time and enough energy to move about and arrange themselves in their least energy positions or their most favorable positions, one would end up with a semiconductor lattice that is almost perfectly crystalline. So, for example, if you look at your silicon wafers, the silicon atoms are allowed to arrange themselves into a periodic lattice, and they are grown from a melt, and they are given, and the growth is done very slowly. So, you are given the atoms enough time and enough energy. But on the other hand, if you do not give enough time or do not give enough energy to the atoms, for example, if you take the melt and you suddenly quench it, you will end up with a material that is quite disordered. The atoms did not have enough time and energy to end up in their least energy positions, and they instead formed a network of randomly arranged atoms, and these atoms could have different bond lengths, they could have different bond angles, etc., and they form a solid, but it is not a crystalline solid. So, you end up with materials that are amorphous in nature. So, generally, okay, and not, I mean, there are examples to counter this. Generally speaking, the nature of the semiconductor that is used in the development of these kind of MOSFETs is amorphous. Okay, so, you end up with an amorphous semiconductor or a non-crystalline semiconductor that forms becomes a part of these devices. And since these devices are based on thin films, these are also called as thin film transistors. Okay. So, they are field effect transistors, but they are just built in a different way on different substrates and are called as thin film transistors or TFTs. So, you might have heard of TFT display, and that is what this refers to. Now, the general architecture of a display is like this, okay, as shown here. You have gate drivers and you have data drivers, but you have the display has got many tiny pixels, okay, and the size of these pixels determine the resolution of this display. And inside this pixel, inside each pixel, you basically have a switch, a capacitor, and a say a light modulating material. Okay. Now, the light modulating material could be an LED, it could be an LCD, wherein the LCD crystal is oriented in accordance to the brightness that we need, etc. But the switch is most often a thin film transistor. Okay. So, this switch capacitor circuit is almost a fundamental building block of any active matrix display system. Okay. And therefore, if one looks at a display screen, the number of pixels present there is equal to the number of transistors present in the display. For a simple system of this kind, of course, you could have larger thin film transistor circuits in each pixel. And in general, this larger electronics has led to a lot of interesting development in the area of displays, in the area of energy storage systems, in the area of wearable electronics, and since all these transistors can be grown on flexible material, mechanically flexible materials such as plastics, you could also have electronics that you can bend and flex. So, the amount of applications or the creative use of these kind of systems is quite large. The application space is quite large. So, now that we have seen how a thin film transistor is grown, what is the problem, what are the materials used, what are the problems, and what are the advantages? The advantages clearly are that all the deposition, etc., can be done at relatively low temperatures as compared to crystalline silicon. On the other hand, this comes with a lot of problems. Okay. Now, before we understand the problems, let us look at the typical materials that one could use. For in terms of inorganic, some of the common semiconductor materials that are used are amorphous silicon, and hydrogen is added to amorphous silicon to passivate some of the disorder, particularly dangling bonds. You could also have polysilicon, which is much better in terms of performance, but still less compared to crystalline silicon. And you also have amorphous metal oxides. Okay. So, for example, zinc oxide or gallium indium zinc oxide, etc. And the semiconductor materials booklet is not limited to just inorganic materials. You also have organic materials, say for example small molecule organic materials such as anthracene or rubrene, and you also have long chain polymer like organic materials. So it is a quite a large set of materials that one could choose a semiconductor from. Now nevertheless, in all these cases we have some very fundamental limitations, and the biggest limitation comes in the form of the mobility of carriers. Now since we are talking about a disordered material, we find that the effective mobility of your electrons in the material is quite low. So just to give you a comparison, here is a comparison of crystalline silicon with amorphous hydrogenated silicon. So you have a field effect mobility for your transistors. Okay, the electron mobility in the case of crystalline silicon is greater than 1000 centimeter square per volt second. Okay, whereas in the case of amorphous silicon it is less than 1 centimeter square per volt second. So which means that the speeds are about 1000 times slower. On the other hand, the on currents, okay, and therefore the on currents in the case of crystalline silicon are about 1000 times larger than amorphous silicon. So you have currents of the order of milliamps in the case of transistor that is on, whereas in the case of amorphous silicon the currents are of the order of microamps for a transistor that is on. The operating voltages or the voltages required to create the field to make these electrons move is again, you need much smaller voltages in the case of crystalline silicon. Whereas in the case of amorphous materials the voltages do vary from say anywhere between 5 volts to 20 volts, and this very much depends upon your process, the device structure, and the nature of the semiconductor, and particularly the semiconductor insulator interface and the contacts. And in crystalline silicon we have both NMOS and PMOS transistors, which means you have a complementary metal oxide semiconductor process, whereas and we saw that this has a lot of advantages when it came to circuit design, particularly in the development of amplifiers. Whereas in the case of amorphous semiconductors, most of the time, or in the case of most of the materials, practically speaking we only have N type transistors or we only have P type transistors. So most of the organics give you P type transistors, and say amorphous silicon for example gives you N type behavior, and we do not have complementary MOS transistors in most materials. But having said that, there are also several organic materials that allow you to have both N and P type transistors, which means you do have a CMOS process in these materials. So let us now look at the consequence of the structure of crystalline and amorphous materials, and what the consequences with regards to the density of states. Now in the case of crystalline materials we had a periodic lattice, okay, you had a nice arrangement of atoms, and we did have defects but those were quite rare, okay. And because of this nice arrangement of atoms, we saw that we could use the Kronig-Spenny model, and we could use the Bloch's theorem, and all that led us to the fact that we have several energy levels and we have clean energy gaps between these energy levels. So we had a forbidden gap, and that was very clean. And in terms of the density of states picture for crystalline, for 3D crystalline materials, we saw that we have the valence band edge, that was the conduction band edge, and we had a density of states that varied as the square root of energy, square root of E minus EC and the square root of EV minus E in the conduction bands and valence bands respectively. That is, we had states in these regions, and then we had a band gap with say a band gap of energy Eg, and in the band gap there were absolutely no states. Okay, so this was the density of states diagram for a crystalline material, and what this meant was that if you want to count the number of carriers say the number of electrons inside the band gap, the number of electrons is dependent, okay, at any energy level E is dependent on the value of the Fermi function at that energy level into the density of states at that energy level dE, and so this is the number of electrons per unit volume. And although the Fermi function had a value that was between 0 and 1, the density of states had a value of 0 inside the band gap, and therefore this product was equal to 0. Okay. So, in other words, there are no electrons to be found in the density of states. However, if say due to a defect, if a few states appear in the band gap, it is possible that it is possible for us to find electrons at these energy levels depending on the value of the Fermi function and the number of states that appear. So, this was the story in the case of crystalline silicon or crystalline semiconductors. Now, the story in case of amorphous semiconductors is quite different. Okay. So, here we could draw. So, this is the example, this example is shown for amorphous hydrogenated silicon, okay, but there is something equivalent for any amorphous semiconductor. So, we could draw something equivalent to our conduction band edge, and we could draw something equivalent to our valence band edge, and this is the plot of the density of states versus energy for an amorphous material. So, the first thing that one observes is that there is no clean band gap. Okay. So, here is your conduction band edge, here is the valence band edge. In the case of crystalline materials, this entire region was void of any states, but in the case of amorphous materials, you find that you have a large number of states. So, you have states throughout the band gap or throughout the energy distribution. Okay. So, it becomes quite hard to state as to which is the conduction band edge and which is the valence band edge. So, you have states throughout distribution. Okay. That is the first point to notice, and the only definition for what constitutes the conduction band edge and what constitutes the valence band edge comes from the definition of the mobility of carriers, and we will come to that in a minute. So, it is generally seen that carriers sitting above EC move a little faster as compared to carriers that are below EC, and therefore, all these states that are sitting above the conduction band edge and below the valence band edge are also called as extended states, okay, and we will talk about this in a minute. So, now let us focus on the states inside the band gap. Now, this dotted line here indicates the Fermi level position. Now, all these states that are present in the band gap and that lie above the Fermi level are called as acceptor like states. Now, these are called acceptor like states because they are neutral when they are empty, and the moment an electron occupies these states become negatively charged. Okay. And the states that lie below the Fermi level are called donor like states. So, they are neutral when they are filled with an electron, and the moment an electron leaves them they become positively charged. There are two further classification of the states in the band gap. The states that are located near the band edges, okay, so that is these regions here and these regions here, are called as tail states or band tail states, okay, and the states that are located in the middle of the band gap, that is closer to mid gap, are something called as deep defect states or deep states. Okay, so, therefore, one can have acceptor like band tail states that are basically the states here. One can have acceptor like deep states which are basically the states here close to the mid gap, but above the Fermi level. One could have donor like deep states which are the states located here, and one could have donor like tail states which are essentially the states located here. So, these are the definitions of the these are the definitions associated with the density of states diagram for amorphous semiconductors. So, a key idea with regards to understanding the behavior of carriers in amorphous materials is defined by something called as Anderson's theory of localization. So, in the case of crystalline materials, we found that the crystalline material had a very periodic potential well, which we used in our model, which was called as the chronic penny model, and we used along with the Bloch's theorem. We found that the electrons the electron wave function could propagate through the lattice. Okay. Although there were very clean gaps which the electron could not possess, the electron wave function extended through the lattice, and we had and it permitted electron conduction through the solid. But in the case of amorphous materials, we find that the potential well has got varying levels of disorderness. Okay. So, you have the floor of the potential well that is quite disordered, and in some sense the material is not periodic, or the potential well is not periodic. So, as a consequence of that, we find that in Schrodinger's equation, your potential energy term is no longer periodic, and as a consequence of that, you find that there are two possible states in which the electrons could exist. The electrons that stay above your conduction and valence band, which we defined as the extended states, have a wave function that actually propagates through the solid. Okay. Whereas the electrons that are sitting inside the gap states, inside the band gap, they have something called as a localization of the wave function, and what that means is that if you look at the amplitude of the wave function, you find that the amplitude the amplitude of the wave function is quite large at certain points and is negligible at other points, which implies that the probability of finding the particle at these locations is very large, and therefore whereas the probability of finding the particles in the other locations is very small. Therefore, the electrons could be thought of as just particles that sit inside, that remain trapped inside these particular states, and they are not available for conduction in the material. Now, all this is a consequence of the disorderness of this potential, and this happens this is a direct consequence when this disorderness crosses a certain threshold. So, that is what Anderson's theory tells us. So, to summarize the different conduction mechanisms in an amorphous material, all the electrons or all the carriers that sit above the conduction bandage are said to be sitting in the extended states, and these electrons are available for conduction, and you can define a certain mobility for these carriers, and you can define their transport in a manner that is similar to what was defined in the case of crystalline materials. But all the electrons that are sitting in the trap states, which is basically the band tail states or the deep defect states, these electrons are more or less trapped, okay, and they are not available for conduction in a manner as seen in the case of electrons in extended states. And the only way these carriers can move about is via tunneling or via a mechanism called as hopping. And a general nature and a general method or a model that describes the transport of carriers in trap states is as shown here. So, you can imagine two trap states, okay, and these electrons have got a certain wave function, and this wave function is heavily localized, so it has got a very large amplitude that sits very large amplitude at around these locations, and the probability that an electron moves from state 1 to state 2 or vice versa is given by P12, and this probability depends upon the distance between these states as well as the energy differences between these two states, and it depends as the exponential of the negative of the distance and the exponential of the negative of the energy, which implies that if these states are very far apart or if they are located, they have very large energy gaps between them, there is a much smaller probability of the electron actually getting from state 1 to state 2. Now, with regards to the electron movement in the extended states, the movement can be thought of as shown in this picture here. Okay, so, you have, so let us say that is the conduction band edge, and all these states are the extended states. And below the conduction band edge and very close to it, there are the trap states that would try to trap the electrons and hold it and localize them. So, the movement of the electron in the extended states is described as something called as a multiple trap and release model. And what happens here is that the electrons move quite quickly in the extended states, and they have some mobility called as mobility of mu naught. Okay. Now, once in a while the electrons get trapped in these trap states, and they spend some time in these trap states. But if the electrons are trapped in trap states that are quite close to the extended state edge, which is close to EC, a small amount of energy can release these electrons. Okay. So, let us say a small amount of thermal energy allows these electrons to get free from this trap state and get back into the extended state. So, the movement of the electron is a periodic is a sequence of extended state transport and then some amount of trapping, wherein the electron spends some time in the trap states and then gets free again and then moves through the extended states and then gets trapped again, etc. And therefore, one can define, if one defines the extended state mobility of the carriers, okay, which we call the free carrier mobility as mu naught, then the effective mobility that one sees for carriers moving in a disordered material is say mu d, which we will call as a drift mobility, and that mu d is given as mu naught into the time spent by the carriers in the free states divided by the total time spent by the carriers in the semiconductor, which is basically a summation of the total time spent by the carrier in the free states plus the time spent by the carriers in the trapped states. So, this is the definition of the effective or the drift velocity or the drift mobility of carriers, and this is the mobility definition that we would use while trying to define the drift velocity of the carriers. So, just to summarize, okay, so everything we have seen so far. So, we see that we want amorphous semiconductors for applications in say larger electronic systems or wearable electronic systems, etc. And the consequence of amorphous semiconductors, the consequence of the disorderness of the lattice is that you have, firstly you have states in the band gap. Okay. So, the band gap is not clean, you have states in the band gap, and therefore, you have carriers trapped in the band gap. And if one is interested in calculating the carrier concentration inside the gap, then we just need to define the density of states in the gap and multiply it with the Fermi function. Okay. The third consequence is that the carriers in the gap, okay, so the carriers can either be in extended states where they have a mobility say mu naught, or they could be trapped in the gap, which are basically a localized states where they are trapped, and these carriers do not in any practical sense contribute to conduction in your semiconductor devices. And the carriers that are present in extended states can move with an effective velocity given by the drift mobility, defined by the drift mobility, which is nothing but your extended state mobility into this ratio, which is the ratio of the time spent by the carrier in the extended states divided by the total time spent by the carrier in the material, which is your T free plus T trapped, and this is defined by something called as the multiple trap release mechanism. So, this is a summary of everything we have looked at so far.